In a hydraulic system, pumps are used to pressurize the fluid and create flow. These pumps take hydraulic fluid from a reservoir on their inlet or suction side and force it out the pressure side to the rest of the system, where it can be used to perform work. In this lesson, we are going to look at what happens at the suction side of a pump. But before we can understand how the suction side of the pump works, we must understand atmospheric pressure. Normally, we think of air as being weightless, but actually it does have a weight. Imagine air as blocks piled up on the Earth's surface. This pile of air is exerting a pressure on everything, every rock, every plant, every square inch of your body. You can't feel it, but it's there just the same. So how much pressure does this pile of air exert? One way to determine that is to close one end of a glass tube and then fill it with mercury. Now we invert the tube in a bowl of mercury. The only thing that can affect how much mercury remains in the tube is the pressure of the atmosphere on the mercury in the bowl. In fact, we can actually determine by measuring the height of the mercury in the tube just how much pressure is exerted by the air piled upon the Earth's surface. As you can see, the column of mercury is approximately 30 inches. Actually, it's 29.92 inches under normal conditions at sea level. If we tried the same demonstration on top of a mountain where there is less air piled above us, we would find that the mercury would not rise as high in the column. That's because there would be less atmospheric pressure available acting on the mercury in the bowl. 1 inch of mercury exerts a pressure of about 1/2 pound per square inch. Therefore, 30 inches of mercury exerts a pressure of about 15 pounds per square inch. That's the approximate pressure exerted by the atmosphere at sea level. Atmospheric pressure can be stated either in inches of mercury using the letters Hg, the chemical notation for mercury, or in pounds per square inch, which is usually shortened to psi. Most gauges used to measure pressure in a hydraulic system indicate the amount of pressure above atmospheric pressure. This is called gauge pressure, or psi-G. The actual pressure is really gauge pressure plus the atmospheric pressure and is referred to as psi-A, or pounds per square inch absolute. In a hydraulic system, pressure is created at the outlet side of a pump, but the inlet side of the pump creates vacuum, the opposite of pressure. Vacuum is usually expressed in inches of mercury vacuum. To explain vacuum a little better, let's place a hollow glass tube in a bowl of mercury. Since the air in the tube is under the same atmospheric pressure as the mercury in the bowl, no mercury is being forced up the tube. With a vacuum pump, we can pump some of the air out of the top of the tube, creating a partial vacuum. Now the atmospheric pressure in the tube is less than that pressing on the mercury in the bowl, so the mercury is pushed up the tube, in this case 10 inches. So we say we have 10 inches of mercury vacuum. Exactly the same principle is used when you drink a soft drink with a straw. You create a partial vacuum in the straw by lowering the pressure in your mouth below atmospheric pressure. The result is that the atmospheric pressure pushes the liquid up the straw. Remember, the numbers on a vacuum gauge read in inches of mercury vacuum. That means they indicate how much less than atmospheric pressure, how much suction, is on the inlet side of the pump. A 0 reading on a vacuum gauge then corresponds to atmospheric pressure, 14.7 psi, or 0 suction. Now let's look at a simple hydraulic pump and see how pressure and vacuum affect its operation. When the rotor turns, the vanes, which are free to move in and out, are forced outward against the outer ring by centrifugal force. As the rotor turns, this space gets larger, creating a partial vacuum on the inlet or suction side of the pump coming from the reservoir. Because there is less pressure here, atmospheric pressure in the reservoir will push the fluid into the suction line and up into the pump, just as we saw with the soda straw a moment ago. The pressure applied to the liquid by the atmosphere is used in two ways. First, it moves the liquid from the reservoir up the suction line to the pump inlet port. And secondly, it's used to force the liquid into the pump to fill the moving rotating group. If moving the liquid from the reservoir to the suction port requires too much of the atmospheric pressure, for example, when the pump has been mounted too high above the liquid level in the reservoir, there is not enough pressure left to force the liquid into the rotating group fast enough. Leading pump manufacturers give their suction specifications in terms of vacuum at sea level. If a pump manufacturer specifies that no more than 7 inches of mercury vacuum be present at the pump's inlet port, this means that only 7 inches of the available atmospheric pressure should be used to get the fluid up to the port, in order to have the remaining atmospheric pressure available to push the fluid into the rotating group. So, if we put a vacuum gauge on the suction side of the pump and find the vacuum to be more than 7 inches of mercury, we are likely to get erratic operation, and we could even damage the pump. If a pump is to be used at an elevation higher than sea level, say at Denver, where the atmospheric pressure is about 5 inches less than at sea level, the lesser atmospheric pressure must be taken into account. The reading should be approximately 2 inches. This is because we started out 5 inches of mercury short due to the difference in elevation. Pump specifications are normally given for a pump operating at a certain speed and using a petroleum-based fluid. Therefore, the specification must be altered if a different speed or a different fluid is used. For example, if a fire-resistant fluid is used, the difference in the specific gravity of the fire-resistant fluid will affect the pump's maximum allowable inlet vacuum. A fluid's specific gravity is a comparison of the weight of 1 cubic foot of the fluid to 1 cubic foot of water. A cubic foot of water weighs 62.4 pounds at 60 degrees Fahrenheit. An equal amount of a commonly used petroleum-based hydraulic fluid weighs 56.4 pounds at the same temperature. If we divide the oil's weight by the weight of the water, we get the specific gravity of the oil. Most pumps give the maximum allowable inlet vacuum based on petroleum fluids. However, fire-resistant fluids can weigh more than petroleum-based fluids. Before changing fluids in a system, be certain the fluid you choose will not exceed the pump manufacturer's inlet vacuum specifications. Otherwise, a problem called cavitation could occur. Cavitation is the formation and the collapse of cavities, holes, within the fluid. These holes are created when the fluid boils, not from heat, but from low pressure. When the pressure at the suction side of a pump is too low, in other words, too much vacuum is created, the fluid will actually begin to boil at normal operating temperatures. When that happens, gas-filled cavities form in the fluid and interfere with proper lubrication. The cavities also destroy metal surfaces, especially on the outlet side of the pump. As the cavities in the fluid are carried to the outlet side by the rotating group, the pressure on them suddenly increases. The cavities collapse with tremendous force. Continued cavitation will ruin the inside surfaces of the pump, even releasing metal particles that will be carried by the fluid to other components throughout the system. Cavitation is the reason why, when choosing or installing a pump, it's very important not to exceed the pump's inlet vacuum specifications. Doing so will probably cause cavitation. Similar problems can be caused by air getting into the system at the suction side of a pump. If air gets into the suction line, for instance through a loose fitting, it can form bubbles in the fluid. This is referred to as entrained air. These undissolved bubbles are carried along with the fluid. Bubbles in the suction side of the pump have much the same effect as cavitation. However, since this is not associated with a liquid's vapor pressure, we call this pseudocavitation. Pseudocavitation is often mistaken for cavitation. Most of the time, however, you can tell if a pump is cavitating or just sucking air by the sound it is making. A cavitating pump makes a steady, high-pitched sound, while a pump that is sucking air will sound erratic, with rattles, bangs, and popping noises. If you are not sure what the problem is by listening to the sound, take a vacuum reading at the pump inlet. Compare the reading to what the manufacturer's specifications call for. If the reading is too low and the pump is making erratic noises, chances are good that the pump is experiencing pseudo-cavitation. If the reading is too high and the noise is not erratic, it's probably cavitation. On new systems, cavitation is often the result of poor suction line design or fluid with the wrong viscosity. Cavitation on older systems, however, is often caused by a plugged suction line or a dirty inlet filter. Now, there's one final thing to keep in mind about the suction side of a pump: priming. Priming a pump means filling the pumping mechanism with fluid. If it's not primed, it is full of air or air-bound. This air must be removed or purged from the pump and the suction line before the pump can be safely operated. Running an air-bound pump for even a few minutes can seriously damage it from the lack of lubrication. Most hydraulic pumps make poor air compressors and have a difficult time pushing air past any kind of resistance, like a pressure relief valve. Often, the easiest way to purge the air from a pump is to run the pump outlet directly back to the tank unrestricted. This can often be done by opening a valve or two so only a little pressure is needed to get fluid through the system, then jogging the pump until it fills with fluid and is operating correctly. This concludes the lesson on the operation at the suction side of a pump. In the next lesson, we'll examine how hydraulic actuators convert fluid pressure into mechanical energy to perform work.